I'm Dr. Mahmoud Abdul Salam by name, and I welcome you to the continuation of this class in PLV Virtual Library. The last time we stopped at alpha decay under radioactivity. Today we are going to continue, and we're going to look at the rest of the emissions. Last time we've seen alpha, and we've seen how alpha changes the atomic and nuclear number after whenever a radioisotope emits alpha particle. We have seen the possible energy that can be emitted whenever a particle, a radioisotope emits alpha. We calculated the Q value. Today what we are going to look at is we are going to look at the emission of beta and gamma particle. Okay, beta ray and then alpha, beta ray and then the electron. So I think I will start with the gamma ray and then the beta particle. I think I will start with beta particle. As established, beta particle is negatively charged. They are electron in nature. They have small deflection. Remember, when we are talking about alpha particle, we said it suffers large deflection in electric or magnetic fields. And in this case, we said it suffers small deflection in electric or magnetic fields. As we said, since it's electron in nature, you know it has negative charge of -1. So whenever a particle emits beta particle, and a radioisotope emits beta particle, it's expected that the charge of the particle is going to increase by 1. Since this one is -1, we said that the total number has to be equal. For example, I have 5x here, now emitting beta particle, which is -1e. So it means this number is going to increase by 1 on the other side, which is going to be 6. Is that understood? So that's what we mean by the number is going to increase, the charge number is going to increase by 1. Please, are we in the clear regarding this beta particle? Alright, now regarding the gamma ray. Gamma ray, it has no charge. It suffers no deflection in electric or magnetic fields. When you try to block gamma ray, you find out that it cannot be blocked unless if you're going to use lead. If you put in like these walls that we are having, a gamma particle will automatically pass through. It will pass across. Is that understood? So it means it cannot easily be blocked. Is that understood? So far, these are some of the properties of this radiation, and there is not going to be change in the atomic or mass number of a particle by releasing gamma ray, because gamma is a ray. It has no charge, it has no mass. So you don't expect the charge number to change, you don't expect the mass number to change if a particle is to release gamma emission. Is that understood? So with this in mind, the next thing that we need to consider to look at is natural and artificial radioactivity. Some elements are naturally radioactive. You get the element, you keep them here, they will start emitting this particular radiation. Some you have to bombard them. You have to target them with a metal, with possibly, let's say, neutron. Those that are naturally radioactive are what we call natural radioactive materials. The artificial radioactivity is, for example, if you bombard uranium with a neutron. By targeting uranium, for example, you have uranium-23592, you direct neutron 0N, it will now give you a new product. Is that okay? So the new product is simply depending, it can form number of products. Is that okay? And the new product, this is now what we call artificial radioactivity, because we artificially entice the element to start emitting new particles. Is that understood? So with this in mind, please, do you have any question regarding this? Any questions so far? So with this in mind, the next thing that we are going to look at is radioactive decay law. What do we mean by radioactive decay law? We're going to try and see the relationship between, we're going to try and see the rate at which these particles are disintegrated. How does the initial element present affect the rate of decay of these elements is what we are going to look at. Is that okay? And then the radioactive decay law is expressed in calculus notation. I believe we are all familiar with the principles of calculus, where it says the rate of disintegration, dN by dt, is directly proportional to the number of elements present. Let's understand what this relationship is trying to tell us. Is trying to explain to us the rate at which these radioisotopes are disintegrated. For example, if let's say you have 25 grams of uranium, or let's say plutonium disintegrated, you don't expect to have the same rate of disintegration when you have, let's say, 10 grams. Is that okay? So what this relationship is saying is that the rate at which there is disintegration, rate of disintegration, dN dt, is proportional to the number of elements initially present. Is that okay? So now let's do this. The initial number of products, suppose we call them N naughts. Is that okay? And we have this. Normally for mathematics, we cannot use proportionality constants to do calculation. Is that correct? We have to change it. We have to use, change it to an equation. And what we can say is that dN by dt is going to be equals to minus, let's say, lambda N naughts. Is that understood? Where minus lambda is simply proportionality constant. I can simply say that dN dt is equals to proportional to minus N naughts, simply to indicate that the number is decreasing with increase in time. Is that understood? Is that understood? So with this in mind, I'm now going to try and change the mathematical format of the equation in such a way that I can use it for simple day-to-day mathematical calculations. How do I do it? I can simply say that dN by N is going to be equals to minus lambda dt. N naught is just a notation. I can write it anyhow I feel like. You understand? It's simply indicating the number of elements initially present. Is that understood? Is that understood? Remember, for me now to get rid of this dt, I have to invoke calculus. And to do that, all I need to do is to integrate both sides, because I'm having dd, rate of change, derivatives. Is that okay? The differential calculus. So now I have the integral of this and then the integral of this. Am I with you, please? Am I with you? Normally, if I have the integral of, let's say, dx all over x, what is going to be the integral? Dx over x, integral of dx over x. You just did calculus. Have you forgotten your calculus? Sorry? Did you do something like this? What is the integral? Sorry, what is the integral? Okay, here I'm having dn over n, which is similar to dx over x. And I believe you come across something like this. Did you do it? Did you do it? Please flip through the pages, get the answer. Okay, if you have this, the answer here, what we have is what we call ln x, otherwise log base e of x. Did you remember it? Did you do something like this in calculus? Did you do something like this in calculus? Yeah? but you can't remember it. So now what we have here is we have ln n equals to the dt. Once you integrate dt, you're going to have lambda t. Okay? But normally there is going to be, because the reaction now is going to, okay, we are talking about disintegration, is going to start from a given number to a final number. Initially what you are going to have, you're going to have let's say initially you're going to have n naught, the initial number of atoms present, and finally you're going to have n. Is that okay? So in here I can say that this is going to be equals to n naught and this is going to be equals to n, and in here I'll put in the lower limit and then the upper limit. Is that okay? I don't know, but I think it's like this. So now, this is log, right? So I can simply write this as log n base e minus log n naught base e is going to be equals to minus lambda t. Is that okay? And I can simply write this as log base e using laws of logarithm. If I have log a minus log b having the same base, I can say that it's going to be the log of this divided by the log of this, right? So I'm going to say n all over n naught equals to minus lambda t. Is that correct? So I can simply say this is log, right? If I have log p base 10 equals to x, I can say that p equals to 10 raised to the power of x. Can I do this? Using laws of logarithm. If I have log p base 10 equals to x, then 10 raised to the power of x is going to be equals to p. Is that true? So what I'm trying to do here is to say that n all over n naught is going to be equals to e, because in here what I have is minus lambda t. Am I with you? So that n is going to be equals to n naught e raised to the power minus lambda t. Is that okay? So this equation, what is telling me that is that if I have the initial number of atoms present is n naught, after a time t, I'm going to have n, where lambda is called decay constant, which is constant called decay constant. After a time t, I'm going to have n, and this is what we call radioactive decay law. Is that understood? Have not this at the back of your mind. This equation is very important. If, for example, in the next 1 million years to come, somebody who doesn't know the age of this building can come for carbon dating, this is one of the equations they can use to know the exact age of this building. They use it in carbon dating. If somebody is to die somewhere, doctors have no idea of the time of his death. They can come and ascertain the time of the death, even if nobody is there when he died. And part of what they use is this. Is that okay? So this is radioactive decay law. N is the number of atoms present after a time t. N naught is the initial number of atoms. E is a constant, exponential function. Lambda is decay constant and t is time. Please, if this understood, please. Is it understood? No? Where do you have problem? Here. Here. Do you have problem with this point, please? You understand everything? Is there anyone that has a problem somewhere again? Is there anyone that has problems somewhere again? All right, now let's look at this. What do we have here? Okay, in here what I did is I substituted the upper and the lower limit. The upper limit is n. So what will happen in calculus is going to be the upper limit minus the lower limit. So it's going to be the ln of the upper limit, which is the ln of n, minus the ln of the lower limit, the ln of n naughts. So this is log n minus log n naughts. Normally in logarithm, what you do is when you have log a minus log b, all you need to do is use laws of logarithm, and it's going to be equals to log a all over b. So it's going to be equals to the log of b, the log of e, n all over n naughts. Is that understood? The log of n all over n naughts. And now that I have this, I'm still going to use laws of logarithm, because in laws of logarithm, if I have log p base 10 equals to x, it means 10 raised to the power of x is going to be equals to p. Similarly, if I take this e and raise it to the power of this, is going to be equals to n all over n naught. And that's what I did here. So I multiply throughout by n naught, I obtain here, I obtain this. And this is what we call the radioactive decay law. Lambda is radioactive, the decay constant. T is time. N naught is initial number of atoms present, and n is the final number of atoms after a time t. Are we there? Did you understand it? So now I'm going to use this to establish what we call half-life. What we call something half-life? By half-life we mean a time where a radioisotope is going to decay to half its original mass. Do you understand what I mean? By saying half its original mass is, initially you have 24 grams. It will start decaying. By decaying, the mass will keep decreasing and decreasing and decreasing. Eventually, at a given time, only 12 grams will be present. Is that okay? For an isotope to decay to have the original mass present is what we call the decay, the half-life. Is that okay? So half-life is defined as the time it takes a radioisotope to decay to half its original mass. Half of 24 is 12, right? Half of 24 is 12. So if I have this equation, at half-life, n is going to be equals to n naught all over 2. Is that okay? Because at half-life, when it was 24, I have 12. And 24 divided by 2 is 12. Is that okay? And then t is going to t half. Because now I'm going to call it the half-life. Is that understood? So now, at half-life, I'm going to substitute this, and then I will obtain an expression for the half-life. My n is n naught over 2. So I have n naught all over 2. It's going to be equals to n naught e raised to the power minus lambda. And I said that at half-life t is going to be equals to t half. I said at half-life t is going to be equals to t half. So now this is going to be equals to t half. Is that okay? So can I say that, look, can I divide throughout by n naughts? Can I divide throughout by n naughts? Can I? Suppose I said this times 1 all over n naughts. This times 1 all over n naughts. Did I do anything wrong? Is it mathematically correct? Yes. Is it mathematically correct? Okay. So this will cancel this. This will cancel this. And I have 1 all over 2 equals to e raised to the power minus lambda t half. Is that okay? Is that okay? Can I call this to be equals to 2 raised to the power minus 1 equals to e raised to the power minus lambda t half? Can I do that? Because 1 over 2 in index form, 1 over a is a raised to the power minus 1. Is that true? So having said this, what I can do is I can take the ln of both sides, the log base e of both sides. So that log base E of 2 raised to the power of minus 1 is going to be equals to log base E of E raised to the power of minus lambda T half. Still, using laws of logarithm, I can say that minus ln 2, because log base E is ln 2, is going to be equals to minus lambda T half log E base E. Is that true? Because using laws of logarithm, I can take this to the other side, and it says, simply say is log E base E. Is that true? What is log E base E? Log E base E is what? Log 10 base 10 is what? What? Log 10 base 10 is 1. So log E base E2 is 1. So that means this guy, I have only minus lambda T half equals to, okay, lambda, because I have minus ln 2 equals to lambda T half. Is that true? So that T half will be equals to ln 2 all over lambda. Is that understood? So now all I need to do is, okay, this is what gives us the expression, the relationship between the decay constant and the half-life, because ln 2 is constant. I use your calculator. Punch ln 2, log 2 base E. You're going to have 0.69, I think 03 all over lambda. 0.693 or 0.6903. Ln 2 log base E. Can I have the calculus? It's taking you time. Come, let me show you. Come. This is ln 2. Let me do it again. This is ln. Okay? Ln 2. Go and press it. Ln 2 is what?
0.69.
Okay? You see, it's very simple, right? All right. So now, this expression, this relation gives us the relationship between the half-life of any radionuclide and the decay constants. Is that okay? So now, having established this, the next thing that we're going to use is, we use this simple relationship to do some simple calculations. Okay, we do one, I think we have this, right? So we are going to use this and then we do the calculation. Can I clean here? Please, can I clean here? Okay. We have a radioactive sample which contains 2.5 milligram of pure iodine, iodine 131, which has a half-life of 8 days. T half equals to 8 days. N naught equals to 2.5 milligram. Okay? Are we there? It says what fraction of iodine would have remained after 16 days. Look, this iodine is going to be disintegrating, all right? Right from D1, it will start disintegrating. We are now interested in calculating the iodine that is going to remain after 16 days. So what we need to do is, we apply the relationship which is available before us, and then we establish what is going to remain. The equation says N equals to N naught E raised to 4 minus lambda T. Is that okay? Is that okay? But do you know lambda? Do you know lambda? We don't know lambda. But we knew that T half equals to 0.693 all over lambda. We knew that, right? So we can say that lambda is going to be equal to 0.693 all over T half. Is that okay? Whenever you are going to do this kind of calculations, note the standard SI unit of time is in second. So all your time need to be in second. Okay? So you may need to convert 8 days into second. But for the purpose of this calculation, we are not going to do that. The reason why we are not going to do it is because this is in days, this is in days. Whether we do, and this one too is in days, whether we do the conversion or we didn't, the final answer is not going to affect our conversion because it's all in days. But the SI unit of time is in second. It's good that you always write the time in second. So now, this is going to be equals to 0.693 all over the half-life is 8. Divide 0.693 by 8. Zero point 8086625. Okay? Are we happy with this? Now, this is our lambda, and we are now back to this. N is going to be equals to n naught e raised to 4 minus lambda t. And this is going to be equals to, look, they are asking us of the fraction that is going to remain. There is a way we can do the calculation, because n naught is the initial number of atoms present. Is that true? So we can simply say that it's going to be equals to n naught e raised to 4 minus, this is our lambda, 0.086625 times time. The given time here is 16. Is that okay? So times 16. And this is going to be equals to n naught e raised to 4 of minus 683. Yeah. Lokaci yayi? Bari da mangama. Okay, if you multiply this by this, what did you get? Did you multiply them? Zero 86625 times 16. What? Oh. 0.086625 times 16. 1.386. Is that okay? All right. So you have that answer. Can you press negative? Change the answer to negative. Let me have the calculator, please. Because sometimes, I don't know, you don't know how to punch the calculators.